Assalamualaikum and very good day to all. Today we're going to proceed our topics in wave propagations, but now for today we will focus on wave propagations in lossy dielectrics. Yeah. So the objectives of today's lesson is to study the wave propagations behavior in lossy dielectric in terms of intrinsic impedance. Okay, in terms of intrinsic impedance. Where is my pointer? Okay, here. In terms of intrinsic impedance, wave velocity, wave number, which is also known as propagation constant, and relation between propagating electric field and magnetic field. So these are all we have learned or we have seen in previous lecture. However, but in a different medium. Okay, in previously we discussed this in terms of free space and lossless dielectric, right? So today we're going to look into lossy dielectrics. So before that, I would like to recall what we have learned in our previous lecture. Alright, so in our previous lecture, if you still remember, the intrinsic impedance. Okay, let's go one by one. The intrinsic impedance. Okay, I hope you still remember. Okay, let's recall it together. The intrinsic impedance for the previous class is, so let's continue. The intrinsic impedance, if you still remember from our previous class, for a free space medium. Okay, for a free space medium, intrinsic impedance is given to us as equals to mu naught over epsilon naught, right? Where the value is constant, which is because this is a constant value and this is also a constant value. Therefore, the intrinsic impedance for a free space is also a constant value. However, the intrinsic impedance for a lossless. So what you have to do, you have to modify this equation. So therefore, it's going to be mu naught mu r over epsilon naught epsilon r, or also it can be written as mu over epsilon. Okay, mu over epsilon, and this value is not constant. It based on what kind of material of dielectric that you are using. All right. So today we're gonna expand this in terms of lossy dielectric. Okay, for lossy dielectric, we're gonna look this today. Okay, so this is for the intrinsic impedance. How about for wave velocity? Okay, for wave velocity, in our previous lecture, okay, for a free space, yeah, for a free space, the wave velocity is given to us as velocity is given to us as the velocity of, yeah, it can be represented as u, okay, or v. Sometimes we are using v, velocity. Okay, either u with a vector above or v. You can use either one here. So the free space, the velocity is constant, which is the velocity is given to us as 1 over mu naught epsilon naught, where this is also known as the speed velocity of light. Alright, the velocity of light, which is the value is also constant value, which is 3 times 10 to the power of 8 meter per second. Okay, so this is for a free space. How about for a lossless? Okay, for a lossless, you have to modify this equation. Okay, either u or v. Yeah. So how to modify this equation? It can look mu over epsilon, or this also can be rewrite as mu naught mu r epsilon naught epsilon r. Okay. and you will get one value here. Okay, so this is for the lossless. And later on for today, we're going to look for lossy. Okay, lossy. Now let's go to the propagation constant. Okay, for propagation constant, okay, for a free space, propagation constant K naught, yeah, is equals as omega mu naught epsilon naught, right? Or it also can be written as omega over c. What is c? C is a speed of light, yeah, speed of light. Okay, so this c also shows the speed of light. Okay, but then how about for the lossless? So for the lossless, you have to modify this wave propagation. So there were going to be no naught here. It's only k. So omega mu naught mu r epsilon naught epsilon r. Okay, so this is the value for the lossless. And today we're going to later on, we're going to see for the lossy. Okay, so this is the wave number and the relation between the propagating electric field and magnetic field for free space. Okay, the relation we have looked before, which is given to us as relation, yeah, Ex, the amplitude, yeah, of electric wave over the amplitude of magnetic wave is equals to mu naught over epsilon naught. This is for the free space. But then for a lossless, yeah, for a lossless, it will then be same amplitude of electric field over amplitude of magnetic field. Okay, but then mu over epsilon, mu naught, mu r, epsilon naught, epsilon r. Okay, and today we're going to later on going to see the relation in terms of lossy. So this is a fast recap what we have learned in our previous lecture. All right. So today we're going to look the same thing but in different medium, which is the medium is lossy dielectric. All right. Okay, so now let's recall what is lossy dielectric. Okay, so the concept has been discussed. If you still remember, we have discussed this in terms of displacement current. All right, displacement current. So the lossy dielectric, we did know that the permittivity is complex. Okay, the value of the permittivity is complex, where it's given to us as such. Okay, you have look this equation in our previous lecture, yeah, where in our previous lecture the epsilon prime 1 minus j sigma over omega epsilon prime. Okay, we have discussed this in our previous lecture. So this can be written as such. All right, so this and this is same. All right, and where this E is E naught ER, yeah, epsilon naught epsilon R. So this is same, yeah. So epsilon C is referring to the complex dielectric permittivity, and epsilon is referring to the dielectric permittivity in real component. I'm so sorry, this is a spelling mistake, real component. And sigma is referring to the dielectric conductivity, and omega is frequency in radian per second. Okay, so today we're going to expand this knowledge. We're going to see in terms of wave propagations. Okay, how we want to discuss the lossy dielectric in terms of wave propagations. Yeah. So the plane wave in lossy dielectrics. Yeah. So to know this, let's recall what we have learned in lossless dielectric. So this is what we have learned in lossless dielectric, where the propagation constant, okay, for a lossless, yeah, not for a free space. Okay, this is for lossless. It given to us k is equals to omega mu epsilon. all right? And where this mu, I think I don't have to mention this every time here. I think you can get this by yourself now, yeah? However, in a lossy dielectric, our epsilon now is in terms of complex, and therefore our K also will be in terms of complex. Okay, why it is a complex number? It depends. It's based on this, yeah? Because of our epsilon is in terms of complex number, and our K is also in terms of complex number. And therefore, okay, what gonna be? Okay, since that our epsilon now is in a complex number, therefore it is a natural mathematics. Therefore, our K also going to be in a complex number, right? So we have to do alterations for this equation number 2, right? So therefore, from equation number 2, our K now, okay, to find the propagation constant, okay, our epsilon, our mu are going to be the same. Okay, our epsilon now we have to replace with complex number. So it's going to be epsilon minus j sigma over omega. And this, I think I don't have to show to you this. You can prove this by yourself. Okay, can also be written as such. Okay, I'm so sorry. This is only one sigma. Yeah. I hope you can correct your slide. Okay. All right. Sigma over omega, epsilon. All right. Where this epsilon can be epsilon naught, epsilon r, epsilon naught, epsilon r, mu naught, mu r. Okay. All right, so I think you can prove this by yourself. You don't have to worry. This will gonna be given to you during in exam in your final exam. Okay, so from here, from K later on, okay, from K later on, we need to expand, okay, where since that it is a complex number, yeah, since it is a complex number, we will transform this equation to be a complex number. So it's gonna looks like this, yeah, jk is equals to alpha plus j beta. So what is alpha and what is beta? Okay, so this is we need to investigate, yeah, what is alpha and beta. So K here, this equation, you can rewrite it as such if you multiply with another J, right? You can rewrite it as such, and from here you can expand to be look like this. I think you can do this by yourself. Okay, this is just mathematical approach. Okay, nothing special here. All right, so from here, okay, from equation of 3, yeah, from equation number 3, if you substitute inside here, we can rewrite to be as such. Okay, omega squared mu epsilon prime minus j omega mu sigma. Okay, you will get then equation number 5. So from equation number 4 to equation number 5, then you can separate it to be a real number and the imaginary part, the real component and the imaginary component. All right, so the real component can be written as equation number 6 and the imaginary component can be written as number 7. Okay, so therefore equation 6 and equation 7 are used to determine, okay, we're going to later on use this equation 6 and equation 7 for you to determine the alpha and the beta. Okay, we're going to expand what is alpha, what is beta. All right, so alpha, what is alpha? Alpha is known as attenuation constant. Okay, alpha is known as attenuation constant, and the formula is given. This formula, yeah, is actually we get from this both equation. We can rewrite as such. Okay, where it is omega square root of mu epsilon over 2 bracket, and then square root of 1 plus sigma squared over omega squared epsilon squared minus 1. And the unit, this is the unit, yeah? The unit is given as Nappers per meter. Okay, Napper, yeah? Napper per meter. Okay, Napper per meter. So you don't worry with this equation. This equation will be given to you in your exam. So don't worry about this equation. All right. So what is attenuation constant? Attenuation constant measure the wave attenuation while traveling in a medium. Okay, what is attenuation actually? If you still remember, when we discussed about lossy dielectric in our previous lecture, we know that lossy dielectric, if we draw the equivalent circuit, it contains of resistor, and it contains of I see, this is ID, displacement, resistor, and this is contains of capacitor, where the resistor is from the conduction current, right? From the conduction current. And the resistor and the capacitor is from the displacement current. So we know in our lossy dielectric, there are two types of currents exist, the conduction current and the displacement current. And the conduction current, if we draw the equivalent circuit, it is represented as resistor, and resistor produce heat, right? Resistor produce heat, and also the currents here is known as a leakage current. Okay, a leakage current. So from here, the heat and this leakage current here is known as loss. This is known as loss in our in the circuit. Okay, therefore we know in a lossy dielectric there is a loss occurred. Okay, there is a loss occurred, and that loss, okay, to measure how much of this loss occurred is by this attenuation. Okay, so attenuation will determine how much loss occurred in wave propagating dielectric in a lossy medium. All right, I repeat it again. Attenuation measure or determine how much loss, okay, how much loss occurred in wave propagating dielectric. So that is what we need to know. We need to know how to measure the attenuation constant inside here. Okay. All right. So that is alpha. Now let's go. What is beta? Okay. So now you already know what is alpha. Yeah. You already know what is alpha. So now let's go to beta. What is beta? Beta here is known as, okay, beta here is known as a phase constant, and it is given as such, where the unit is radian per meter. So you don't have to worry, this equation also will be given in your exam, but then you have to understand what is beta. So beta is a phase constant. So what is a phase constant actually? Phase constant measure the phase change while traveling in a medium. Okay, while traveling in a medium. So due to this attenuation, due to there is a loss appear or occurred inside our circuit, so therefore the phase also, okay, the wave phase also will be changed, of course, and it will change by time when it traveling in a lossy medium. All right. So I think for a phase constant here, the symbol is quite different between our free space and lossless, where the phase constant for free space and lossless is measured, okay, propagating, or also known as a phase is measured as K, right? But then for a lossy, our phase constant, okay, our phase or propagating, okay, propagating constant is represented as beta. All right, so don't get confused with that, but it shows to the same meaning, a phase or propagating constant. Okay, now you already know what is alpha, you already know what is beta. So now let's recall from our previous lecture the wave propagation equation. Okay, this is I think I have shown to you this equation in our previous lecture. Okay, that the wave propagation can be written as such, where this referring to the positive z direction and this referring to minus z direction. So what is the meaning of positive z direction and negative z direction? Of course, the direction is different. Negative z direction is referring to the reflected wave. For example, you have a wave that reflected, that move, that propagates along positive z direction, of course, there will gonna be another wave that is reflected it again. So this wave that reflected it again will be in negative z direction. Okay, negative z direction, right? So since that there is no loss in our free space and our lossless, in our lossless medium, so we assume that we consider, that the reflected wave to be same as propagating wave, but then the only difference is the direction, okay, in different direction. Okay, all right, so where k is a wave propagation constant in lossless dielectric, k here, all right. Okay, so for a lossless dielectric, so you will not represent as K naught, you will represent it as K only, all right? So we want to observe here in terms of lossy dielectric. How about lossy dielectric? So for lossy dielectric, we need to replace this JK, we need to replace this JK with alpha plus J beta, and therefore it will becomes as such as equation number 11, where this is the positive z direction and the negative z direction. Okay, positive z direction and negative z direction, and negative z direction referring to the reflected wave. Okay, reflected wave. And in this lecture, okay, in this chapter, to make our study simplified, let's ignore this let's ignore this reflected wave. Okay, let's ignore this reflected wave. Let's ignore it and we just discuss about the propagating wave, because our interest now is to look at the propagating wave. Okay, and we are ignoring the reflected wave. Okay, so now consider a wave propagation in positive z direction, positive z direction, and we ignoring this minus z direction here. So this equation can be written as such, can be written as such, where you expand this exponential component inside here to be the real component and the imaginary component. So in real component, okay, if we are taking only the real component here, it can be rewrite as such, because we know j theta is equals to cos theta plus j sin theta, right? And this, I think I have explained in our previous lecture. We also ignoring this part, the imaginary part. We are taking only the real part, okay? So we can rewrite it as such, Then to compare, okay, before we go there, let's compare this with a lossless medium. This is for a lossy medium, right? So now let's compare the equation with lossless medium, where the lossless medium is given to us as such, from our previous lecture, beta z. Okay, beta z. Okay, so we can see here the amplitude now. Let's see. The cos is same, This is the same. But now the difference is only at the amplitude part. Okay, this part is different. Where in a lossless, where we know, by the name, we can straightforward say to us that for a lossless there is no loss, So therefore the amplitude is definitely without any loss, It's given to us as EX only, without any loss. However, in a lossy, okay, as I mentioned earlier, lossy, there is a loss, okay, and we can see here from the amplitude also, there's an exponentially decay, EX exponential to minus alpha, alpha z. So what is this tell us? It shows to us this, shows to us that the amplitude of wave reduce, is reducing exponentially. Okay, the amplitude of electric wave in our lossy medium is reducing exponentially. All right, where there's no loss or no reduction in lossless. Yeah, so this is the difference between lossy and lossless. All right, so if we can draw, okay, if you want to draw the graph, yeah, Ex, and this is the propagating direction. So your graph are gonna look as such, yeah. It's decaying exponentially, where Ex plus minus alpha z, and alpha is given to us the attenuation value, yeah, the attenuation value that we discussed just now. Okay, and later on, yeah, if you proceed later on, it will this exponential, yeah, will becomes zero, okay, and will become zero, and we can say that the wave is disappearing. Okay, so if the higher the value of attenuation, okay, the higher the value of attenuation, the wave, yeah, will be decaying drastically. All right, the higher the value of attenuation, the wave will going to be decaying drastically. All right. So now, from equation number 13 here, from equation here, number 13, yeah, a wave here will be attenuated. Okay, wave will be attenuated by exponential of minus alpha, where alpha is the attenuation value, when propagate in the lossy dielectric. And here I'm comparing between a free space and a lossless and the lossy graph. So for free space and lossless, okay, the amplitude of the graph will be no changes, yeah, will be no changes. It will give as Ex only. However, in lossy, since that there is an attenuated, it is attenuated, you can see that the amplitude, yeah, is decaying exponentially, where at this part and this part, the exponential, the amplitude is different. Okay. Okay, now in lossless, now let's look into intrinsic impedance. Yeah, in a lossless dielectric, the intrinsic impedance is given to us as such, where we have discussed this in our previous lecture also, where it's given to us a real value. Okay, the value is a real value number. However, in lossy dielectric, okay, since that our epsilon is in terms of complex number, therefore, the intrinsic impedance also will be in a complex number, where it will contains of imaginary and real component, right? So the intrinsic impedance later will give to us as such, okay, as such, where the value, the amplitude, yeah, the amplitude of intrinsic impedance will be much lesser compared to the phase, okay, compared to the phase, and the value is given to us as such. So you don't have to worry about this, yeah, this is going to be given to us, it will be given to you in your exam. Okay, so how to measure the intrinsic impedance amplitude for lossy dielectric? So this is the formula. Okay, the formula will be given to you. All right, you don't have to memorize this formula. All right, but what you have to know is you need to know how to use this formula. Yeah, so this mu will then referring to mu naught mu r, epsilon naught epsilon r, and same goes to here. Yeah, epsilon naught epsilon r. Right? So now, if you want to see the relation between the electric field and the magnetic field, if you want to see the relation between electric field and magnetic field, okay, this is the relation in our lossless, yeah, lossless. However, in the lossy medium, the relation later on will give to us as such. Yeah, so we can see here that the E, okay, the electric field and the magnetic field have a different phase based on a value of theta. Okay, value of theta will give a different phase between magnetic field and the electric field. And if we can, okay, if we can draw the graph later on, yeah. Okay, our magnetic field will be given as such, yeah. And if we can draw the graph, for example, this is X, this is Y, and this is Z, okay. The electric wave will give to us, the electric wave is is polarized along X, right? So it will give to us as such, and it is decaying by time, right? Then the magnetic wave. Okay, let's change the color first. The magnetic wave is at y-axis, yeah, polarized at y, and also decaying by time. So it's gonna look like such. Okay, so you can see here that our H field and our electric field is differently, yeah, have different propagations, yeah. Different phase, yeah, not different propagation. I'm so sorry for that. Yeah, different phase, yeah. The phase is not same. Okay, so previously in lossless dielectric, the wave velocity. Okay, now we are discussing about the wave velocity. The wave velocity for a lossless dielectric is given to us as such. Yeah, the velocity is equals to omega over k, where for a free space, the velocity is equals to the velocity of light. Okay, the velocity is equals to the velocity of light, right? in a lossy dielectric, okay, in a lossy dielectric, the wave velocity will then, instead of k, okay, the phase constant has been the symbol of phase constant in lossy dielectric is given to us as beta, right? So you just have to change, yeah, omega over beta. All right, so I think this is my last slide. So in conclusion, for wave propagation in a lossy dielectric, there are two important observations that we can make. First of all is both electric and magnetic field wave will be attenuated, okay, will be decaying by exponential of attenuation, yeah, minus alpha z. And the second observation is electric wave E is leading the magnetic wave H by theta. Okay, electric wave is leading the magnetic wave by theta. All right, so I think we're gonna stop it here. Okay, later on in our next class, okay, we're gonna have another last class, right? Next week before the revision week. Okay, in our next class, okay, we're gonna look one example for this, and also we will discuss about the last topic, which is the pointing vector for wave propagations. All right, so thank you very much and see you next class. All right.